Now we're ready to look at the fourth conic section. So we already had parabolas, circles, ellipses, and now on to hyperbolas. And you've already seen hyperbolas in Chapter 9, but we're going to look at them in a little bit different context. So before I read through the definition with you, I'm going to quick show a picture, and then this definition will make more sense. Here's an example of what a hyperbola looks like. You're not used to the hyperbolas opening to the left and the right. You're used to them being set up where they're in maybe one quadrant over here and another quadrant over here. But now our hyperbolas are going to look like this. We are going to have two asymptotes for each hyperbola that we have, and we will have vertices. As you would kind of expect, these points will be called vertices, and there will be two foci. And our definition of a hyperbola will be if we have a point who is on the hyperbola, and we'll call him point P. If we have a point who's on the hyperbola, we will measure the distance from the point to one focus. We'll call him f sub 1. And we measure the distance to the other focus. Let's see if I can draw that line. Oh, that's not too bad. And the difference, absolute difference between those two lengths, so we would take this length, use the distance formula and find that length, minus this length, and that would equal a particular value. And it ends up on a hyperbola regardless of what point you pick. So here's another point. This distance and this distance, if I subtract them, will always be a constant. Doesn't matter how far away I go. I can go way up here and take this distance and this distance, subtract those two measures, and that difference, the absolute difference, will always be a constant. Okay, so let's look back. That's what the definition says, that a hyperbola is a set of points in a plane such that the absolute value of the difference between the distances from the point who is on the hyperbola to two fixed points, who are going to be called our foci, is a constant value k. And that is a P right there. So the difference between the point, or the distance from the point to one focus, find the distance from the point to another focus, the difference between those in absolute value will always be the same value. Remember, with an ellipse, it ended up that the sum of those ended up being a constant. In our case, we have the absolute difference being a constant. And so we have our two fixed points are the foci. The transverse axis is, let me pull this picture back up, the distance between these two vertices is called our transverse axis. This little distance will actually be, if this is the center, this little distance will actually be our little a. This little distance will also be little a. Again, that's the center. These would be vertices. We have our two foci. And then it ends up this distance from the center to a focus will be C. And you can see that's longer than A. Same idea here. That's long. Whoops, that should be a C. Distance from the center to a focus is our little c. So we use little a's, b's, and c's in this type of a conic section as well. We will also have asymptotes, and we'll get back to that in a minute. But the equations, if we have our hyperbola centered at 0, 0, will look like this form. And haven't even talked about what the little b looks like yet, but that's our setup. Now, equations, when the center of the hyperbola is at 0, 0, are going to look like either this form, so you should jot that down, or this form, and that is a 1. So they kind of look similar to an elliptical form, except we do see that we have a subtraction sign. And we have the ability for standard form to have the x term in the front. This will open left and right. And we have hyperbolas who open up and down. This form, when the y is the lead coefficient, ends up opening up and down. And I remember this because I think the x-axis is an axis that goes left and right, and hyperbolas that start with an x squared are going to open left and right. And likewise, same thing, a y-axis goes up and down, and if our y is the lead value, then our hyperbola will open up and down. So it's pretty easy for me to remember by just looking at those variables and thinking what the axis does. Now, this picture is going to look a little bit complicated initially. Told you that the hyperbola opens left and right. Now, let me grab a sheet of paper and I'll actually redraw this so that it will make more sense. When we have our hyperbola of x squared over a squared minus y squared, whoops, sorry about that, y squared over b squared equals 1. This lead coefficient of a squared, we will use the square root of it, or a, and in the x direction, we will move out a unit. So I'm just going to make it look like a is 4 units, but naturally a can be a lot of different values. So whatever this number is squared, square root it, and in the x direction, because we have it underneath the x variable, we move out a units. Now, underneath the y variable is a b. We move b units in the y direction. And so I'm going to make that look like it's 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. This guides us to be able to make a little rectangular box that is going to be our guideline. And so we make this little rectangular box. And so again, I went a units out in the x direction because the x had the a squared term underneath it. And in the y direction, I go b units up, b units down. Now the next thing I need to do is I need to make diagonals for this box. These are going to end up being our asymptotes. And in fact, I'm going to write the equation of the asymptote right now. I can see it's centered at 0, 0, and this was b units up, so I go up b over a. So this has a slope of b over a x, and the y-intercept is 0. So there's the equation of that asymptote. As opposed to this asymptote, I can see it has a negative slope because I have to drop down b units and then run over a to get the slope. So down b over a. This equation has y equals negative b over a times x. And again, my y-intercept is 0, so I have my asymptotes. Now, remember, look at that lead variable. The x variable on your x-axis is where your vertices are. This point is a vertex. This point is a vertex. And then we will just eyeball. We could plot points and be more accurate, but we're going to use those asymptotes to guide us and draw the hyperbola like so. This axis from this vertex to this vertex is going to end up being our transverse axis. You can see this was a units long, this was a units long, so the transverse axis would always be 2a units long. This is not a point on the hyperbola. This is not a point on the hyperbola, but it definitely was being used to make that box to allow me to get those asymptotes. Now, if our equation is in this form, I probably could turn the video off and just let you draw what you think is going to happen here. And that x squared looks really weird, doesn't it? Let's erase that and make him look better. There we go. Notice I'm always having this lead have the a squared term underneath it. So this is the only conic section that we're allowing the x and the y to switch, because that negative sign doesn't allow me to switch these around. I want the positive value to be here in the front, so I have to put that y squared in the front. All the other conic sections will always have the x term in the beginning for the ellipses and the circles. Now, ready to draw this one. Now in the y direction, I'm going to move a units up. So let's say I call that a. And in the y direction, I'm going to go a units down. In the x direction, I'm going to go b units to the right. And in the x direction, I'm going to go b units to the left. I draw my box exactly the same way I did the others. And the variable that has the coefficient underneath, you will always be doing that movement for that one. But now I'll draw my asymptotes in, those diagonals of that box, and I'll write the equation. To get the slope of this, it's still going through 0, 0, but I go up a and then right b. So this is going to have a slope of a over bx. This equation is a negative slope, I can see, and I go down a over b. So I get that. And now I look at that variable again. Got to be careful you don't make the mistake of drawing it the wrong way. This is not on the hyperbola. This just helped me find the box. This is not on the hyperbola. It just helped me find the box. In the y direction, so up and down, these are my vertices right here. And we'll just eyeball in and try to stay inside those asymptotes, and I have my hyperbola. Okay. All right, so now let's practice on this one down here. And they're really not too hard to graph. And let me kind of erase my graph over that function. All right, so we know that the equations all have to be in a form where this coefficient is a 1. Ellipses and hyperbolas have to be put into that standard form to graph, and we need these last coefficients to be 1. So I can see on my example, I'm going to need to divide everything by 64. And I'll do it right here. Okay, so when I reduce that down, wow, that lead just shot out of there. Okay, so I have x squared over 16 minus y squared over 4 equals 1. Now, I can see right now that this is going to open left and right because I have my x variable at that front position. These numbers are going to guide me to make my box. I know this guy is a squared. I know that guy is b squared. So if that is a squared, I know a is equal to 4. And if that's b squared, I know that b is equal to 2. Now, in the x direction, I'm going to move 4 units from the center. And the center is here. I'm going to use 4 units this way. And I'm going to move 4 units this way. 1, 2, 3, 4. These will be vertices. The transverse axis will be 8 units long. Now I'm ready to make the other part of the box. I have to go up 2 units. He's not on the hyperbola, and 2 units down. These are my guidelines to help me make that box so I can make those asymptotes. So, dot them in. Make those diagonals. Now we're going to find the equation of those asymptotes because we need to practice that. And let's find this one first. It doesn't ask to do that, but we might as well. I have to go up 2 over 4, so I have a slope of 1/2. This one, I have to go down 2, right 4, so that has a slope of negative 1/2. Don't forget to put the x there because otherwise it will be a horizontal line. And now I'm ready to graph my hyperbola because I know in the x direction this is going to open left and right. This is not part of the hyperbola, remember, that just helps me to make the box. So I'm going to have kind of a skinny guy over here and another skinny guy over there. Okay. Now there are foci, and we haven't even brought that idea of the foci up yet, but we'll bring that part up now. So let me kind of flip over to the next example because we're talking about it here. It says finding the foci of a hyperbola. So we have a graph and we can see, oh, this has that y squared term at the front as opposed to the x squared term at the front. So we have to graph this and we have to find the foci. And then we'll go back and label on our other little diagram where those foci are located and what the relationship is between the A, B, and C. All right, so we know, and I'm just going to write this over a little bit bigger here. Okay, so this is always my a squared. So a is 2. So I'm going to move in the y direction right now because that is over the y, or the a is underneath the y, I should say. And so in the y direction, I have to move 2 units. So I move up 2 and down 2. And these will be vertices. Whatever that lead is, that's what's going to determine where your vertices are. And this is my little b squared, so I know b is 3. And so I need to move in the x direction. I need to move 3 units to the right and 3 units to the left. These are not on the hyperbola. They're guidelines for my box. All right, I'll try to keep my hand kind of out of the way. Being a lefty, kind of hard to do that. But there's my box. Now I'm going to draw my asymptotes. Once again, we weren't asked to find the equation of the asymptotes on this. It said to find the foci, but we're going to do it anyway. I got the rise over the run. I rise up 2, run over 3. So I've got y equals 2/3 x. still centered at 0, 0, so I don't have a y-intercept. And naturally, we can see what this one's going to be. Go down 2 over 3, so y equals negative 2/3 x. Okay. All right, and now we can graph this. So we don't really have to have the foci graphed in order to graph this, but we'll get the foci afterwards. And remember, in the y direction, my hyperbola is set up y-axis up and down. That's what's going to happen with my hyperbola. So this one's kind of flat looking. Okay, now let's find the foci. Now, the foci, just like in a parabola, that we can kind of think that the hyperbola is kind of hug the foci or the focal point. And so there's going to be a focus up here someplace and a focus down here someplace. And the relationship between these is, you're going to kind of like this one, is that a squared plus b squared equals c squared. This is my little distance a. This is my distance b. And actually, see this little diagonal here in the center? This little diagonal is actually how long c is. And so we can determine what that c squared, or the c value, is, and then we'll be able to move from the center up c units to find where that focus is. C is always longer than both a and b, because again, here's little a, here's little b, and really this diagonal, this is also little a. So this is little a, this is little b. This is actually the length of little c. If I could just take a little compass and go deet, 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 I could actually place and plop down where it is. But let's plug the numbers in. We know that a squared is 4. And we know that b squared, as this number, is 9. So actually we know that c squared is equal to 13. That's the exact value. So c is the square root of 13. Let me just grab my calculator here and quick do square root of 13. As a decimal, that comes out to be approximately 3.6. And so I know my focal point up here would be, if I move 1, 2, 3.6, is about right there. The exact value of that focus, so this is like, I'll call them F1, the exact value is, the x-coordinate is 0, the y-coordinate is square root of 13, which again is approximately 3.6. If I'm going to graph it, I'm going to use the decimal approximation. And then the other focal point is down here, 1, 2, 3, there's negative 4, so right about right there. And that is the second focal point. Now once again, his x-coordinate is 0, and his y-coordinate is negative square root of 13, which is approximately negative 3.6. And what really happens if I pick a point on this hyperbola, this distance, use distance formula, and that distance, the difference between those is always equal to a constant. It doesn't matter if I pick a point way down here. If I measure that distance and that distance and subtract them, that will always equal a constant. Okay, so let's, if you have it, if you figure you've got it, then you don't even need to look at the last example, but I'll do one more example here. Okay, I'm looking at this, it's already in that nice form. I can see that this guy is going to open left and right because of that x squared value being at the front. And this just says find the foci. Let's get those foci just to begin with, and then we'll go through and graph. So remember that a squared plus b squared equals c squared. C is always the longest in a hyperbola. And so I know that this is 25. Make sure you don't square it again. That is a squared. And I have my b squared. So I know c squared is going to equal 34. So c is going to be the square root of 34. And let me get a quick decimal approximation for that. Square root 34, about 5.8. I can give you more decimals, but it's going to be hard to graph that accurately. Now, we're ready to graph. So I know that that is a squared, so a is 5. And it's in the x direction, so I'm going to go out 5. 1, 2, 3, 4, 5. So there, that's going to be a vertex. 1, 2, 3, 4, 5. There's another vertex. And then my box, I need to get B. B is 3. So I know in the y direction I need to move up 3 units. So up to here. Remember, he's not on the hyperbola. 1, 2, 3. I can get my box. I'm sorry, but when I draw these dotted lines, I keep thinking deet, 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 deet. Deet, 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 deet. Deet, 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 deet. Here we go. And now we're ready to draw in those asymptotes. Deet, 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 deet. Deet, 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 deet. Okay. All right. If I ask you to find the equation, again, we would go up 3 over 5. This would be y equals 3/5 x. This one, down 3 over 5. Y equals negative 3/5 x. You weren't asked to do that, but we might as well. Got to draw the graph because it opened in the x direction. Again, we could plot more points and get more accurate, but that looks good. And now let's get the coordinates of the foci. The focal points are always hugged by your hyperbola, just like they're hugged by your parabola. And I have, if I move out 5.8, and this was already to 5 out, so right about there is one focus. And his exact coordinate is negative square root of 34, 0. But if I list it down as negative 5.830, that's plenty good. And the other one is going to be located on the opposite side. And I'd say he's about right there. And so the second focal point would be at positive square root of 34, 0. Or decimal approximation about 5.830. Okay, and you're ready to practice.